All right, guys. So we finished up to 5. We're going to look at 6. Now, this is not going to take too much time. Analyzing graphs of functions. Vertical line test, find the zeros, determine intervals. And up there, well, the graph of function is a collection of ordered pairs. We know this. We've looked at graphs. We've seen graphs up to this point. So this here is just relating x, the distance away from y, and y equals f of x, the distance away from x. And we have this here. Now the domain is the input function, or the values. So what x values do we have across the function? And the range is the y values of the function. And we can also denote f of -1 and f of -2, which is just really telling us, if we wanted to look at those there, f of -1, what is going to be the y value when x is -1? We say f of -1 is 1. We could also do the same thing with f of 2. So we look and see when x is 2, well, the y value is -3. And that's it. I mean, there's not a whole lot to it. We can talk about maximum and minimum. Maximum is going to be the biggest value that we have on the function. We talk about that in terms of y, the y value. So here the maximum would be 3, and it'd be located at the point 0, 3. Our minimum is going to be this here, 2, -3. So that's the maximum and minimum points. And they're extrema because they are the highest and lowest points. We can talk about also having local maximum, local minimum, which means that the function, instead of stopping here, would continue indefinitely this way and this way. Well, these are not the absolute maximum and minimum because the function continues up and down. We call them local because over a certain distance, they are the biggest point or smallest point. Now, the closed dots at -1, 1 indicates that x equals -1 is the domain of f, where the open intervals 5, 2 indicates that x is equal to 5 is not in the domain. So the domain is this here because we can do the same thing we talked through most of this here. The use of dots, open or closed, at the extreme left and right of the graph indicates the graph does not extend beyond these points. By definition, function most y values given x. Now this one here, the vertical line test for a function. This is something we've done before. You've done it in middle school. If you can draw a vertical line and it crosses the graph at more than one point, it is not a function. And that's it. I don't think we have to say much about the vertical line test because we've done it before. We don't need to see it again. Zeros of a function. The zeros of a function are the x values for which f of x equals 0. We're just looking for when it crosses the x-axis. For what value of x will the function be 0? And we could do that with these here. Because if we wanted to go about finding out 3x squared plus x minus 10, I could grab the graphing calculator, clear all these out. 3x squared minus x minus 10. Look back at it, make sure. 3x squared plus x minus 10. This would have given us a completely different function. We can say graph, and we do see that it crosses at 2 points. It crosses the x-axis at 2 points, but we can't draw a vertical line and it crosses at more than 1 point. So it is a function, but we would need to go about solving it. Now, one of the ways we can do that is by factoring, because we're wanting to see where this equals 0. Now, since the 10 is negative, our signs would be positive and negative. Then we're going to look at the factors of 3x squared and 10. Now, the factors of x squared are x and the factors of 3 are 1 and 3. So I just need to pick one of them to put the 3. I'm going to put it in the first. Now, the factors of 10, there's more than one. We have 1 and 10, or which one do we want to try first? 2 and 5. Which one goes first? Okay. 5 is second. Now the last thing we can do is check. Now I normally never check 3x times x, our first terms, because 3x times x is 3x squared. Well, we got that from the factors of 3x squared. We should get back there. I don't always, or I really never multiply 2 and -5, because that'll definitely get us back to -10. The only one that really changes is the middle term. 3x times -5 is -15x. 2 times x is plus 2x. This gives us -13x. So that's not quite. But what we can do is we can flip the 2 and 5 and try again. Because I always try switching the second terms, our constant terms first, before switching the x's. Now, if the x's were just x and x, switching them won't do a whole lot. But we can try this here. 3x times 2 is -6x. 5 times x is plus 5x, which is equal to -x. Is that close? It's the right number, but wrong sign, yes? Whenever we get the wrong sign, all we have to do is switch the signs. Because now 3x times 2 is positive 6x. -5 times x is -5x, which does give us indeed. So these here are our two solutions. At this point here, we're going to set both of them equal to 0. Now our first one over here, we can add 5 to both sides, telling us 3x is equal to almost 5/3. Now the other one, we can subtract 2, telling us x is equal to. So 3/5 is 1 2/3. And if we look at the graph, okay, well the one side of it does cross at about where 1 2/3 would be on the x-axis, yes? If we look at the other point, -2 does indeed cross at the y value of 0. Crosses the x-axis at -2. So we do have those two spots. Now we can calculate a 0. We can go second trace 0. And I'm going to pick a left and right bound. So we know that that spot where it crosses the x-axis is what we want to find. So I'm going to pick a point to the left of it, for the left bound, and right bound, I'm going to pick a point to the right. Since it's going from below to above the graph, the first one's going to be a spot below. The right is going to be one above. If we're going for the other one, we would pick the left above, the right below. Now the third spot says guess. If we wanted to guess the x value, we could at this point to try to see it, or we can just hit enter and let us tell us that it's 1.6 repeating, 1 2/3. Y'all see that there. So this works well, especially if it's not crossing at a whole number, and we have a good idea of what this fraction is, or a good chance to figure it out, because if it could be 1.5. We know what 1.5 is. But if, 1.5, but if it gives us an irrational number, then we're going to have to do a little bit more to get it. Questions on the first one? Well, square root of 10 minus x squared. Again, I can come back over here. Clear. Second square root of 10 minus x squared. Graph. Well, this is still a function, yes? Now, we can go second table, or second graph, which does give us a table. And do get this here? Okay. So it's going from -3 to 3, and we need to figure out if it does have a solution. So we'll set it up. 0 is equal to the square root of 10 minus x squared. If it was one term, yes. But because of the minus, it's not one whole term being squared, so we can't necessarily do that. Well, not necessarily. We can't do that. We have to square both sides first. Now, the square root and square will cancel. telling us that 0 is equal to 10 minus x squared. We don't need the plus or minus because we didn't take the square root of both sides. Now at this point, I can add x squared to both sides, telling us x squared is equal to 10. And lastly, we can square root both sides. Now this time, we take square root of x squared and we get x. But since we took the square root of both sides, we do need the plus or minus. And this here would be square root of 10. And that's as far as we can take it. Because the square root of 10 does not simplify, because the only way it would simplify if one of its products, factors, which is a product technically, is a perfect square. So 4, 9, 16, going on, which it's not. The only factors of 10 are 2 and 5, which are both prime. So this is as far as we can take it. And these are the answers. Now, if we looked back at this graph, at this here, well, we don't see those, right? But square root of 10, if you were to approximate it, I don't know if either one of you. Yes. And has anybody gone over, I don't know if, I think I have with you on how we approximate square roots. Not really. Okay, so if we think of, well, I missed one of the perfect squares earlier. So 10. What is the closest perfect square to 10? Because 4, I missed one after 4. Well, it's close to 8. 8's a perfect cube. 9. Because 2 squared is 4. 3 squared is 9, yes? 9 is the closest perfect square to 10, yes? So that means we use it and then start adding decimals to it. If we're doing it by hand, we would go to 3.5 next. So I could do 3.5 times 3.5. 12.25, that's too big. Then I could say 3.2 times 3.2. Okay, that's closer. 3.1 times 3.1. Okay, so now we're a little bit better. So I can go 3.15 times. Okay, we might go a little bit bigger. 3.17 times 3.17. Okay, that's, and I can start approximating, getting closer to it. But I can use 3 to start with. Now, one of the other nice things about the graphing calculator, if we go second calculate, because last time we used the 0, yes? What's the first one on this? Value. Second square root 10. Enter. The y value is 0, yes? I was just able to check it to make sure. I can do the same thing. Second calculate value. Negative. Second square root 10 is also 0. That's another way to check it. Questions on this here? And the last one. So we're trying to see when this is 0. Now, a fraction, if a fraction is going to be 0, what part of it really has to be 0? The top or bottom? The top. Because if the bottom's 0, that's undefined, it doesn't work. So really the only way for this to be 0 is if 2t minus 3 is equal to 0. Yes? Now, mathematically, we can do this by multiplying both sides by t plus 5. Because that would simplify to 1. And t plus 5 times 0 is, well, so we get to this here anyways. Now we just need to solve. So we can add 3 to both sides, telling us 2t is equal to. is 1.5. You're thinking of 2/3. Yep, so that's it. Questions on these here? I don't think for the most part this isn't anything new. The only thing with this is that t cannot equal -5 because that would cause the denominator to be 0. That would be a vertical asymptote. The horizontal asymptote would be 2. But that's neither here nor there, because we'll go over that more later. The last thing I want to talk about is increasing and decreasing. So we have this here, increasing, decreasing. So a function is increasing on an interval for any x1 and x2 in the interval x1 is less than x2 implies that f of x1 is less than f of x2. Clear as mud? Because, well, obviously we've gone over this before. Have you covered or talked about increasing, decreasing, and constant before? So let's look at this here. So x1 is less than x2. So if I talk about it on a graph, we're just saying x1 is less than x2. x1 is farther to the left than x2 is. So we have this here. F of x1 is less than f of x2. Well, f of x1 is a y value. F of x2 is a y value. And f of x1 corresponds to the x value x1. So what we're saying is that if it's increasing, f of x1's value, wherever it's at, so we'll say here, its y value has to be smaller than f of x2. So the graph should be going. That's all that says. Decreasing on an interval x1 to x2, that x1 is less than x2. Same setup, implies that f of x1, the y value, is bigger than the other one. It's going down. And the last one, constant on an interval. The y values are the same. It's not going up, it's not going down. Over this interval, it's decreasing. Over this interval, it's constant. Over this interval, it is increasing. Make sense? Now, the way we denote it, or the way we talk about it, is in terms of the x's, the domain, okay? So if we look at this here, this first one, from here to here, we can see that the function is increasing, yes? Here to here, it's still increasing. It's at a smaller rate, but it's still going up. Now, it looks like it might stop, but it's actually still increasing all the way up, yes? So we could say that this here is increasing from -infinity to positive infinity. It's increasing for the entire function. There is no spot where it's decreasing. Now, if we look at this, x cubed minus 3x, so they took the same function and added a little bit to it. Now, we always start left to right, so increasing. So here, it's where it goes off the graph. So we're coming up from -infinity, yes? It's still increasing, it's still increasing. But at -1, 2, it stops, yes? So for the first part, well, the smallest value that we could possibly have, because we came from the left side of the graph, would be -infinity. And where did it stop increasing at? At -1, 2, yes? But we only want the x value, which is -1. Now we can increase in more than one spot, just we're going left to right. So from -infinity to -1, it is increasing. Decreasing. Well, at -1, it starts decreasing, and it keeps, change colors, we're decreasing, decreasing, still decreasing, and then it switches, yes. And what number does it switch at? 1, -2, and the value we want is 1. And at 1, it starts going back up. So we union of 1 comma infinity. So it increased, it decreased, and then it. Questions on this so far? Now the 2 points they listed have a special name. They're called turning points because it turned from increasing to or decreasing to increasing. They're turning points. Questions on this so far? Let's look at the last one. So coming from the left to the right, because we're coming up this graph, it is negative infinity to 0. And then what happens at 0 to 2? And then at 2, it starts from 2 to infinity, because we're always just in terms of the x. But that's it. Questions on this here? Yep, relative minimum, maximum. So I talked about this earlier. Relative minimum, relative maximum talks about it when we have a function that ends up going in one direction or the other, or both. So these here are relative minimum, relative maximum, because this function continue on this way and this way. So these here are the two biggest values over their set terms. So from here to here, this is the relative maximum. From here to here, this is the relative minimum. From here to here, this is the biggest point. They're relative to their little areas. Because it could be that this continues up forever and we don't actually have an extrema, an actual biggest point, because it continues up. But these, over the short period of time, are the relative minimum and relative maximums. And that's it. I mean, we could talk about rate of change. That's not too important. Even and odd functions. Now, we consider a function to be even or odd based off of this here. A function y equals f of x is even when, for each x in the interval of the domain, f of negative x is equal to f of x. So if we plug in negative x into f of x, and we get the same function back that we started with, it's even. It's odd if f of negative x is equal to negative f of x. Well, let's look at an example of this. The function g of x equals x cubed minus x is odd. Okay. So to test this and check, the first thing we do is find out what g of negative x is. And to do this, in every x, we're going to replace it with negative x. Now, negative x to the third, anything to an odd power, well, x times x, well, negative x times negative x is positive x, times negative x is back to negative x, and it would be to the third. But realistically, if we have a negative x to an odd power, it's going to stay negative. If it was to an even power, it would become positive. And lastly, negative negative x is plus x. So our g of negative x is equal to negative x cubed plus x. Now, if this had been even, this equation and this equation would be the same. Well, as we can see here, they are not. Now, for it to be odd, we also need to look at negative g of x. Now, at this point here, we didn't change the x at all, so we're going to replace g of x with its function, x cubed minus x. And at this point here, we're going to distribute the negative to simplify. Our negative times x cubed is negative x cubed. Our negative times negative x becomes, so telling us negative g of x is negative x cubed plus x. Well, are these two the same? So that means g of negative x is equal to negative g of x, which makes it an odd function. And that's it. Now, it already told us that this is even, but the main way we can check it, the first thing we would need to do is see what h of So in every x, we're going to plug in negative x. Well, negative x squared, negative x times negative x is just x squared. And luckily, we've actually simplified everything. Is this function the same as what we started with? Yes. So therefore, it is even. And that's all we have to do to test for even or odd functions. Questions on this here? And we can even, odd functions are symmetric to the origin. Even functions are symmetric to the y-axis. They reflect across those. And that's it. I believe you should have more than enough time to finish this in class today.